Good morning. We're going to look at other ways to solve a Laplace's equation. So far, what we have started with was we started with the uniqueness theorem. So, uniqueness theorem assures us that there is a unique solution. Just to jog your memory, what we did in uniqueness theorem was if you have some volume V, which is bounded by some surface S, right? Then if I define del dot E to be some function f of r and curl E to be some function g of r in V, this is within the volume, and if I specify the electric field on the boundary, on the bounding surface on S, then we showed that we can find a unique solution to phi. We can find a unique solution to the potential. That's what was the uniqueness theorem. We did this using harmonics and the mean value theorem. And from that uniqueness theorem, we have seen that we could use del square phi is equal to 0 to impose boundary conditions and obtain potentials in certain cases. For example, we have seen that if I have a spherical conductor, then all the charge resides on the surface. So del square phi inside is 0, and so is del square phi out is 0. And we impose boundary conditions on this. For example, one boundary condition that we imposed was dou phi out by dou r plus dou phi in by dou r is equal to sigma by epsilon naught. We derived these boundary conditions and we were able to solve the problem, but we were able to solve the problem by assuming that this phi here has only radial symmetry, because we are looking at this very specific case of the spherical conductor. So we made the point that phi of r theta phi is essentially only phi of r. It doesn't depend upon theta or phi. That was the case we made, and from there we solved this del square is equal to 0 in spherical polar coordinates, and from there we got that phi of r was equal to c0 by r plus c1. We got this solution because we used only the radial component of it. But what if the potential is not dependent on just r? Let's say what if the potential is dependent on both r and theta? Then how do we solve this? Right, so there we employ another technique called the separation of variables, which is what we are going to discuss today. So our goal is to solve electrostatics as a boundary value problem, and in case of cases where you may have more than just radial symmetry or more than just symmetry along one direction, then how do we solve this is the question, and we're going to do that with separation of variables. So let's take the example in Griffiths. So we're going to solve example number 3.3, and here what we have is two infinite grounded metal plates lie parallel to the xz plane, right? So we have x, y, and z planes, and then we have two metal plates. So one metal plate is here and another metal plate is there, and they are basically stretching out that way, right? So this is stretching out this way, and these metal plates are grounded, right? So there is no charge on the metal plates because they're grounded, and at the left end x is equal to 0, that is here. This is closed off with an infinite strip. So this is closed off with an infinite strip along this, right? Insulated from the two plates and maintained at potential V0 equal V0 y equal to potential equal to V0 of y. So what we are doing is, if you look from the side, what you would see is, you would see one plate at the top, one plate at the bottom, and these two things are connected by some strip. So that's what you would see if you were to look from this side. So and this, whatever this strip is connected, the problem says that it is insulated from the two plates, right? So if it is insulated from the two plates, we have the first plate at x is equal to 0, y is equal to 0, z is equal to 0. That's this point here. And here, this would be, just y would be equal to a, right? X and z are still 0, right? So we have the boundary conditions from here that basically that the potential phi is equal to 0 at y is equal to 0, and the potential phi is also equal to 0 at y is equal to a. This is because the strip that is attached is insulated, so we don't have any potential at y is equal to 0. That's the bottom plate, and y is equal to a at the top plate. But in between that, we have a potential of v0 of y. So in between that, we have a potential of v0 of y when x is equal to 0. So when x is equal to 0, we have this infinite strip. This infinite strip also runs along the z-axis, right? So at x is equal to 0 at the left end, we have the potential is maintained at v0 of y, and obviously the last condition is that this phi should go to 0 as x goes to infinity, right? So as we go here along x-axis, as we go farther and farther, we're going farther away from this one, this potential here, and so that should go to 0. The potential itself should go to 0. So now we have these boundary conditions, and we know that there is no charge on the plates because they're grounded, and so there is no charge within the slot here, right? So if there is no charge, then we know that del square phi is equal to 0, and we have these boundary conditions. So can we figure out the solution? So here, the infinite strip, this infinite strip itself is running all the way along the z-axis. So because this infinite strip is running all the way along the z-axis, our potential is really independent of z. But it still has not just one direction, but x and y dependence. So we have our phi is phi of xy, really. So then we can put this into the Laplace's equation, and what we would get is that, so del square phi is equal to 0. In Cartesian coordinates, we would have del square phi by x squared and d square phi by dy squared, and phi is only a function of xy because the infinite strip in our problem itself runs along the z-axis, and that's why there is no there is no z dependence in the potential. So this is equal to 0. So here what we are going to perform is the separation of variables. That is, we say then that let's assume that phi of xy is equal to something like x of x and y of y. So here we are assuming that we are assuming these type of solutions. If you recall, sometime back we looked at what kind of solutions could exist for harmonics that are solutions to this. We came up with different sets of solutions that were constants, that were linear, and that were products, and that were sum. And if quadratic polynomials and exponential functions, all these things we discussed when we were discussing harmonic functions. So if you don't recall that, please go back to that lecture and do watch it. But what I'm trying to get at is that not all the solutions to del square phi is equal to 0 can be expressed as a product of something that depends only on x and something that depends only on y. We're limiting ourselves to a very finite set of solutions, right? And it doesn't matter to us because although we're limiting ourselves to a finite set of solutions, it doesn't matter because as long as this, whatever this function is, as long as it satisfies this and the boundary conditions, we are assured that that is the only unique solution that exists for this problem from our uniqueness theorem. So that's why now it becomes very easy to find solutions. So I could say that we do know that not all the solutions to this equation del square phi is equal to 0 could be expressed as a product of a function that depends on x and a function that depends on y only, like x of x and y of y. So not all the solutions can be expressed like this. Nonetheless, if we could find some solution of this form, then we could go back here and satisfy the boundary conditions. Then we know that we have a unique solution. So now if I plug this in here into this equation, what I would get is y times d square d square x by dx squared plus x times d square y by dy squared is equal to 0. Now you divide this entire thing by xy or phi itself, then you would get divided by xy. This side remains 0, and these y's cancel out in here, x's cancel out, and what we get is 1 by x by dou square x dx squared plus 1 by y d square y by dy squared is equal to 0. Now if you notice, this term is only dependent on x and this term is only dependent on y. So if a term that's only dependent on x, when you add it to a term that's only dependent on y, you can get 0 only if they both are constants. Right? They cannot have any, this function itself cannot have any x dependence. This function itself cannot have any overall y dependence because they two add up to 0. So each of them must be equal to a constant. And that's what we are going to write on the next slide, that each of them must be equal to some constant, right? Dx squared is equal to some c1, and 1 by y d squared y by dy squared is equal to c2. And we require c1 plus c2 to be 0. So the c1 plus c2 by 0 ensures that del squared phi is equal to 0, right? So now, if you look at these type of equations, in general, you can write d squared x by dx squared as c1x, right? D squared y by dy squared is equal to c2y. This is the capital X. This capital X is the function, little x is the variable, and same thing here. So now these type of functions could have two different types of solutions, right? So we are going to look at what kind of solutions are possible for equations like this, and then we are going to come back to this slide to solve this further. So what we are trying to do is we are trying to address a problem of two infinite plates. We started with the separation of variables. We separated phi into x and y. We equated them to constants, and now what we are going to see is how to solve this kind of an equation and then get back to this place to finally figure out what would be a solution for our infinite metal plate problem. So if I look at a differential equation that looks like this, some constant in general times x of x, this constant, right, it could be positive or negative, right? So let's say, let's say this constant can be expressed as positive or negative k squared. So this constant could either be positive or negative, and we're just writing it as k squared. So this k squared term itself is always positive, so that we can take out this positive or negative dependence outside and divide this into two types of equations. One type of equation is where you have positive dependence, right? That this constant is positive, or another type of equation where this constant is negative, right? So if the constant is positive, you can easily see what would be a nice solution. For example, x of x, if you double integrate it, you can see that something like e to the power kx would be a solution, right? Because if you do dx by dx, then that would give you k times e to the power kx. So if you do d square x by dx square, you would get k square e to the power kx, but e to the power kx is x of x to begin with, so this would be k square x of x, right? So for this solution, you have exponential solution like e to the power kx. Now let's look at the minus sign. If you take a trigonometric function like x of x is equal to sine kx, right? Then dx by um, x would be cosine kx, right? And d square x by dx squared would be minus k square sine kx. And then again, this sine kx is the function x of x, so you get minus k square x of x. Same thing would happen to cosine function, whether you have sine or cosine. You would get ultimately a negative sign here. So for this, you would have solutions as sine kx or cosine kx, right? It's important to know the nature of these solutions because we have to impose certain boundary conditions. For example, sometimes we may have to impose a boundary conditions like when x is going to infinity, our potential should go to 0, right? So if you have something like a trigonometric function, then you know that's not going to work out because as x goes to infinity, the trigonometric function is not going to go to 0, right? But if I have instead of e to the power kx, if I have e to the power minus kx, that would also be a solution because if I have e to the power minus kx, the first derivative is minus ke times e to the power minus kx, and if I do the derivative of it again, I still get the same thing, right? I would just get a negative sign here. And here I would get a negative of negative, so overall it would be positive. So even e to the power minus kx is a solution to this. So if I have a boundary condition that looks like when x goes to infinity, phi should go to 0, then I may be better off picking this kind of a function instead of this kind of function. So if I have to pick this kind of function, then I must have this constant to be positive. Because if that constant is negative, then the solutions would be, if this is a negative sign, then the solutions would be trigonometric, not exponential. So bearing that in mind, let us go back to the equation that we had here. So we are interested in solving these two, and we know our boundary conditions. One of our boundary conditions is that phi goes to 0 as x goes to infinity. So in order for this boundary conditions to work, then we will choose C1 to be negative. Sorry, we will choose C1 to be positive. My apologies. We'll choose C1 to be positive so that we can have a solution that looks like e to the power minus C1x, right? So as x goes to infinity, this would go to 0. And for this, we can choose a sine or a cosine solution. Sine or a cosine solution. So equipped with that, let's see what we have for the specific problem of two infinite plates. So we have essentially d square x by dx square is equal to some k square x, and d square y by dy square is equal to negative k square y. We got this by doing phi of x, y is equal to some x of x and y of y. So the solutions x and y for these equations directly plug into this to give us the potential. And we got these equations by separating the variables in the Laplace's equation, right? And we're choosing this to be positive and this to be negative because we have different boundary conditions. The first boundary condition is phi is equal to 0 when y is equal to 0. And phi is equal to 0 when y is equal to a. There is potential only in the strip, and that is equal to v0 of y, which is at x is equal to 0. And the fourth boundary condition is phi goes to 0 as x goes to infinity, right? We don't have to worry about the y part because the y part is only between v0, between 0 and a. So as long as we satisfy the 0 and a boundary conditions, we have a potential that we're sure will not go to infinity in that sense, like of x going to infinity, right? So then in general the solutions for this are e to the power kx or e to the power minus kx. So we can write a general solution as a sum of a plus b, a linear combination of e to the power kx and e to the power minus kx. Similarly, for this, we have seen that the solutions are sine kx and cosine kx. So in general, we can write the net solution as c sine kx plus d cosine kx. So then in general, our phi of xy within the slot between the plates, so we have these infinite plates that are stretching like this, right? And they're connected by this strip here along the z-axis, and we are looking somewhere in the slot between these plates. That would be equal to x times y. So x is in general e to the power kx plus be minus kx times c sine kx plus d cosine kx. Now we can find the constants by applying the boundary conditions, right? So if we require phi to go to 0 as x goes to infinity, we see that we have to set this term to 0 because e to the power kx would swell up as x goes to infinity. So we set that term to 0. So to have this boundary condition, sorry, this should be sine ky because we're solving for y. I apologize for that. So a itself should be 0 because we have to satisfy the fourth boundary condition that the potential goes to 0 as we go towards infinity, right? And then let's see. Then we have b times e to the power minus kx, c sine ky plus d cosine ky. Right now you can absorb this b into this thing, right? So you would have e to the power minus kx bc times sine ky plus bd times cosine ky, right? So we have bc and bd. So we're just absorbing this b inside, and we're going to call this as the new constant c and this as the new constant d. You can think of it as c star d star if you want. So we then have the solution to be phi of xy is equal to e to the power minus kx some c star sine kx plus d star, sorry, sine ky d star cosine ky, right? Now the first condition is that phi is equal to 0 at y is equal to 0 because the infinite strip, the strip here, the strip is insulated from the top and the bottom of the plate according to the problem. So the boundary condition that we were given were that phi is equal to 0 when y is equal to 0 or y is equal to a. So if phi has to be 0 when y is equal to 0, then this term has to be 0, or we said d star is equal to 0 because cosine 0 is 1, right? So to make phi go to 0, we have to set this to 0, right? And then we have phi is equal to 0 at y is equal to a. So this would mean that we need sine ka to be equal to 0, right? Because this term is not going to be 0 because this term is only dependent on x. So for the total potential to go to 0, this term should be 0, right? You cannot have c star to be 0 because if c star is 0, you have a trivial solution. Everything is essentially 0. So the only other option is have sine ky at y is equal to a be 0 because y is equal to a, we have sine ka is equal to 0. So in general, this happens when ka is equal to n times pi, right, where n is 1, 2, 3. We are not considering 0 because that's a trivial solution, makes everything 0. So k should be equal to some n pi by a, right, where n goes from 1 to 3. That's what these two boundary conditions would yield. So we would have phi of xy to be some c star times e to the power minus kx sine ky, where k is equal to n pi by a, and n goes from 1 to 3, so on and so forth. Now, this is not a specific solution. This is where we stop. We have applied all the boundary conditions, right? We have applied the boundary conditions that we were given. The only boundary condition that we didn't apply is that we are maintaining the potential to be V0y when x is equal to 0. Within that strip, we were maintaining this potential to be V0y. But it is hard to make this, just this term, equal to a particular value of V0 of y. But V0 of y in general is a function of y, right? And here you have some sine ky. So you could think of writing this V0 of y, you can think of this as expressing this in terms of a Fourier series. So whatever the function V0 of y may be, you can express it as a Fourier series. That means you can express it in sines or cosines, and then that's how you can satisfy the third boundary condition, right? So and that's okay, because for example, let's say phi 1, phi 2, phi 3 till phi n are all solutions to the Laplace's equation del square phi is equal to 0. Then if I were to have a new function that looks like alpha 1 phi 1, alpha 2 phi 2, alpha 3 phi 3, so on and so forth till alpha n phi n is equal to 0, then I can take the del square operator. These are just constants, alphas. So I would get alpha 1 del square phi 1 plus alpha 2 del square phi 2 plus alpha 3 del square phi 3, so on and so forth, is equal to 0. But these satisfy the Laplace equation. That means del square phi 1 is equal to del square phi 2 is equal to so on and so forth is equal to 0, right? So these things satisfy the Laplace equation, so that's 0. So the sum is 0. So this linear combination of all these solutions itself is also a solution to the Laplace's equation. And what we got on the last slide is a series of solutions where n can go from 1 to 3, so on and so forth. So in general then, we can write phi of xy as a series going from n is equal to 1 to infinity, some Cn. This is a coefficient that is unique for each n, right? And we have e to the power minus kx, but k is n pi by a. So we have this as the general solution, right? But when we have phi x is equal to 0 y, we want this to be equal to v0 of y, right? So we want this to be equal to n is equal to 1 to infinity. At x is equal to 0, this term is just 1. So we have Cn star sine n pi y by a. So this is the third boundary condition. This is what is going to help us find Cn, right? So the equation that now we have is, we have n is equal to 1 to infinity, some Cn star sine n pi y by a is equal to v0 of y. This is essentially expressing whatever v0 of y is in the strip that is put at the left edge of these two, at the left edge of the metal plate. So we have one metal plate there and another here, and this strip is along the z-axis, right? And this is being maintained at v0 of y, and we're expressing this v0 of y essentially as this Fourier sum. So how do we figure out Cn star? It's very simple. We multiply the entire thing by sine n prime pi y by a, where this n prime in general is different from this n. So we multiply both sides by that and integrate over dy. So we have n is equal to 1 to infinity Cn star sine n pi y by a, right? And then we're multiplying this with sine n prime y by a, right? So this is equal to v0 of y sine n prime pi y by a. So here what you have to note is that this n prime is one specific number. This n prime is one specific number. It is not a series. Here n is going as 1 to infinity, but there is no counter that is on n prime. N prime is just one number. That's why we are able to take it inside the sum, right? It's just a constant. It's multiplying every term. So here you have the same thing. We multiplied this on both sides, and then we are integrating this over dy, right? So we are integrating this over dy. We're integrating this over dy. So then this is a very special integral that you will see again and again. So these are called, sine and cosines are called, orthogonal functions. So a property of these orthogonal functions is if you have something like sine nx times sine mx, and you are going over, say, a region of 0 to a, then this would be equal to a by 2 delta nm. That is, if you have this n and m to be different, their product when integrated would be 0. For example, let's say you have between, let's say this is 0 and this is a, right? So if I take sine n is equal to 1, sine 1x, right? That would look like something like this, right? And if you take sine 2x, you would get 2 of these, right? So if you multiply these two, you would get something like that. So when you integrate, the area under this curve and area under this curve are exactly opposite each other, and integration is just giving you an area. So they cancel out. So that's why we have delta nm. This is the Kronecker delta. So it is equal to 0 if n is not equal to m. So here, for example, n is equal to 1 and m is equal to 2. The integral would be 0 because because of the nature of these functions, right? So uh, so that's how we are going to solve for this equation. So we have a by 2 delta nm here. So I can plug that in here, right? So then I would have n is equal to 1 to infinity Cn star. This integral itself is going to give me a by 2 delta n prime, and that is equal to integral of v0 of y sine n prime pi y by a dy. So, or in other words, this is going to be equal only when n is equal to n prime, right? So for all other n's, this term is 0. So you have only, this will select out only one term here, that is c of n prime. So this implies that c of n prime, c star of n prime times a by 2 is equal to integral of v0 of y sine n prime pi y by a dy, right? So if I rewrite that, then I would get Cn star to be 2 by a integral 0 to a v0 of y sine n pi y by a dy. So given v0 of y, we can determine Cn star by doing this integral. And in general, we have seen that our solution, we were able to express our solution phi of xy as sigma n is equal to 1 to infinity Cn star e to the power minus n pi x by a times sine n pi y by a. So, and we can determine the Cn star using this equation. So for example, if I want C1 star for n is equal to 1, that would be 2 by a 0 to a v0 of y. This is given to us, and this would be sine pi y by a dy. This is a simple enough integral to perform, right? So then this in general would be the solution where Cn star is given by this. And we can write what the Cn star, we can evaluate this integral in general what it is if I choose the potential to be constant, let's say our V0 of y is really just a constant V0, then we can see that Cn star, this is for a very specific case of a constant potential, 0 to a, V0, if this is constant, then we have sine n pi y by a dy. If this is constant, you can pull it out, so you would get 2V0 by a, and integral of this would just give you 1 minus cosine n pi, right? So this would be equal to 0 if n is even, right? Because cos n pi would be 1, so 1 minus 1 would give you 0, right? If not, if it is minus 1, you would get minus 1 plus 1, so you would get 2, so you would get 4 here. Sorry, this would be n pi. So you would get 4 V0 by n pi if n is odd. So then you can write the total phi of xy as 4V0 by pi sigma n is equal to 1 to infinity, right? 1 by n e to the power minus n pi x by a sine n pi y by a. So this would be the solution to our problem. So I'm going to summarize what we have done, and I know that it could be quite confusing to understand different parts, but you also have to go to the textbook yourself and then read the portion in the textbook. Then your understanding would be better. But just to give you a brief idea of what we have done, we started with the problem of two metal plates, right? We have a strip here, and we have to find out the potential in the slot. And so we started with separating this into x of x and y of y. We argued that the potential is independent of z because this strip is stretching out along z. And by choosing this limited set of solutions like we discussed, we were able to get 1 by d square x is equal to plus k square x, and 1 by y d square y by dy square is equal to minus k square y. We got this by plugging this xy into the Laplace's equation, del square phi is equal to 0. And we were able to do that because there is no charge here, the metal plates are grounded, right? And from here, we saw that we could choose, e to the power kx and e to the power minus kx for this. And for this, we could choose c sine ky plus d cosine ky. And then we had four different boundary conditions, that is phi is equal to 0 when y is equal to 0, and phi is equal to 0 and y is equal to a. This is because the strip is insulated from the plates, right? And then we had phi is equal to v0 of y when x is equal to 0. That is the potential of the strip itself, right? And phi should go to 0 as x goes to infinity as you go away, right? And so these were the boundary conditions on y, and these are the boundary conditions on x. And using these boundary conditions, we were able to eliminate some of these constants. We were able to eliminate a, and we were able to eliminate d. We absorbed this b into c and called it c star. And then we found out a general solution for this c star, and we found out a general solution for phi of xy by putting these boundary conditions. And to satisfy the third boundary conditions, we used a Fourier series, and from there we obtained ultimately this solution for phi of xy as n is equal to 1 to infinity, right? Cn star sine n pi y by a times e to the power e to the power minus n pi x by a. So this is in general the solution that we derived. So this is what constitutes the separation of variables. So next time we are going to do another example with separation of variables. We'll do a couple of examples so we get a good understanding of this, and then we are going to discuss how to use image charge method. Thank you.